So this is my lab this week on a spring oscillating in 2 dimensions. My name is Hugh Karzam and I'm in lab section M08. So the main objective of this lab was to create a model that calculates both the x and y positions of a mass as it oscillates, as well as the 3 different energies involved in the system. And then we need to graph all of those quantities and then compare those results to data extracted from the video we were given by Dr. Greco. The main result that I came up with from doing this lab is that since we picked everything to be in our system, there's nothing in the surroundings to do significant work, so our change in energy is 0. So before I could even calculate any of my energies, I first had to find the spring constant and the length of the spring when it's relaxed. These are both the formulas I used to get those quantities, and I just want to specify that on the frequency right here, the number of oscillations is the y component and not the x. And so when I calculated those quantities, I put them into my code right here, and those remain constant throughout the oscillations. And so the relevant physical properties for this lab were, of course, the 3 different types of energy: kinetic, spring potential energy, and gravitational potential energy. And the L that I used in both of my potential energy equations or formulas is the length of the spring measured from the axis or from the origin. So the next part of my code is of the inertial conditions. I had to calculate the energy of the mass initially, and it's important to know that the kinetic energy initially is 0 because the mass is at rest, but there is both spring potential energy and gravitational potential energy, and I calculated that both right here. As you can see, the gravitational potential energy is dependent on the ball's position in the y direction, and the spring potential energy is calculated by subtracting the relaxed length from the length of the string in its original position. And so the next part of the code is basically how I updated the positions throughout the loop. Some important notes is that the work is 0, and the total energy is the sum of the 3 types of energy we're dealing with, and the change in energy, or delta E, is the sum of all of our changes in energies as it oscillates. And then the very last part of the code was how I got my experimental data from my Excel file and using my code to compare it with my model. And so this is what my model looks like after it runs completely. The orange ball represents the position of the mass based off the numbers that were calculated throughout the model, and the blue represents the mass and its positions that were extracted from the video. And as you can see, their trails are pretty similar. It's not quite perfect, but it's pretty similar. And so the first graph I want to talk about is of the y positions of the masses as it's oscillating. The red represents the model, and the green represents the data extracted from the video. And as you can see, they're pretty similar. Their peaks are relatively in the same positions, as well as their valleys, but they're off by a couple of seconds. And the reason that it's in the negative y, or they're all negative numbers, is because the balls are always below our origin. And so the next graph that I'm going to talk about is the x positions. As you can see, those are also pretty similar. The red is the numbers calculated throughout the loop, or throughout the program, and the green is from the data extracted from the video. And those oscillate pretty similar as well. They're off by a couple seconds. And those have both negative and positive values because this ball is oscillating between negative values and positive throughout the oscillations. And then this is a graph of all my energies. The red is of kinetic, the blue is of gravitational potential energy, and the green is of potential or spring potential energy, and they all add up to give us this yellow line in the middle going along the x-axis, which represents our change in energy, and that's 0. And so the what does it mean questions well, the first one asked us to calculate the period of oscillations in the x component and the y component and explain why they're different. Well, I did that for you guys right here. As you can see, the x is 1.8 and in the y it's 1.5, and it's different because of the force of gravity acting in the y direction which is causing the mass to oscillate quicker due to acceleration, and so that's why its period is less than the period in the x direction. So the second question asked us about the work done by the surroundings. Well, since we don't have anything in the surroundings, because we picked our entire system to be the spring, the mass, and gravity, or the Earth, there's nothing surrounding to do work, so work is 0. And then the last question asked us about changing the position to be where the ball is initially, or where the ball is in static equilibrium, and how does that change affect the graphs of the energies. Well, the formulas are still the same, except now we're measuring L is the y position of the mass, and the L is the distance between that position from -0.7, which is where the mass is at static equilibrium. And so now our stretch could possibly be positive now, but our change in total energy is still going to be 0. And I actually couldn't get my model to write or to put out the proper graph, so I don't really have anything to show you guys. But other than that, the change in total energy is still 0, and we now have different L values, so our graphs don't really change much.